Hello everyone, I am Hoang Ta. Today I am going to present to you our work about the larger cognitive process from the combinatorial degeneration. This is our work with the Matthias, Christandl, Omar, Fawzi, and Zuiddam. Our paper is about constructing special combinatorial objects called the cognitive process, which is motivated by a central problem in the communication complexity. Namely, we focus on the multi-party communication complexity on number on the forecast model. Cognitive process object has been much interested with recent year on the some work of Lina, Vitasi, and Stroman in ITCS 2018, and the Lina Stroman in the CCC 2021, and Viola cover on the 2019 on the quasi-random group, and the green in the 2021. In the work of Lina and Stroman, last year they constructed a large cognitive process into the grid by designing efficient and the communication protocol. In our work, we take a different approach by using the algebraic tool. Namely, we make the progress by introducing in this area the method of combinatorial degeneration. In this talk, the first I will present what are cognitive process, and the second I will present our results on the cognitive process. Then I will present more detail our motivation in the multi-party communication complexity. Namely, we'll focus on the EVA function. And finally, I will introduce a combinatorial degeneration method for constructing cognitive process. So, what are the cognitive process? A cognitive is a triple of the points of the form xy, x plus lambda y, and x y plus lambda, which lambda is non-zero. With lambda equal to 0, we call the trivial cognitive. In this cognitive, we have the xy is the center, and the first coordinate when we change lambda on the first coordinate, and we change on the second coordinate on the first point. The cognitive has been studied on the various settings into the grid. If we consider xy in the grid, and if we consider the xy with operation on the finite group G. Here is the example of the cognitive in the 3 times 3 in the grid, 3 times 3. Here we can see here is the center of the cognitive. Then first we change the first coordinate with lambda equal to 1, and second we change the second coordinate with lambda equal to 1. Here is the example of the cognitive in the finite group on the finite view F3, F3 with this center, and here is this center, and we change first coordinate and the second coordinate. A subset of the point in the grid is a cognitive if no 3 points from a cognitive. That means it does not contain any cognitive. So this is an example. The red point here is the cognitive preset into the grid 3 times 3, and the orange point here is the cognitive preset in F3 times the F3. Now we denote the RF with the size of the largest cognitive free subset in grid S times S. For example, in cognitive preset into the grid, here 3 times 3, we have the R of the 3 equal to 5. And in the finite view F3, we have the R of F3 equal to 3 here. So we want to bound the size of the largest corner-free subset in the various setting. For the integer grids, there's the group in 2007 so that the non-trivial upper bound for the largest corner-free set. For the low bound from the Braham construction, the Braham construction constructs largest subset that does not contain 3-point form arithmetic. By using this, we can show that the low bound for the Rn. Recently, by using the communication protocol on the number on the process model, the linear Schaumann so improve the low bound for the Rn, and recent Green also improve the low bound on the Rn by the in the last year. For the corner free set on the grid, namely we focus on the FPN, on the final view FPN. For the F2N, there are some work on Green and the lazy McLean. They show that the non-trivial upper bound for the largest corner free set in the F2N. For the low bound, the work by Lina, Peterson, and Schaumann, they show that the low bound of the F2N is at least 2.x2 power n minus small n, and by the error construction for the cap set problem on F3, we can show that the size of the largest corner set on the F3N is at least 6.6 power n. Our work shows that on the F3N, the R of the F3N is at least 3.39 power n, and on the F3N is at least 7 power n minus small o n. This improves the two best known low bound by the Lina, introducing by Lina, Peterson, and Schaumann, and the by-error construction for the RF3N. So the question here is whether R of FPN equal to P power 2n minus small o n. This is still the open question. Our motivation from the problem in the number on the forecast model in the multi-party communication complexity. In this model, we consider the three-player list and both and shortly each people keep n bit string, and they want to communicate to determine a binary function f. In this model, the player I can see every other data of the other people, but he or she cannot see his or her data. For example, both can see the data of Alice and Charlie, but he don't know his data, and they communicate this by the broadcasting. In this model, you can think that they can drive the data on the spot test. And the objective here, we want to determine the most efficient deterministic protocol for them to determine the value of function f, and we denote this by the d3 of f. The central function in the communication complexity called the EVA function. The function equal to 1 if the sum equal to 0. Here the sum is the sum of the n bit string with plus by each coordinate, we plus the sum of the coordinates on the string. On the two-player down, so that the d2 of EVA function equal to omega n. But for the three-player, the d3 of EVA equal to omega n is still the open question. In the work of Chandra First and Litton, and Lina, Pitashi, and Schaumann. They show that the larger cognitive preset in the F2N times F2N is equivalent to efficient NOF protocol for the EVA function. Namely, if the largest cognitive preset is less than C power n on the F2N, with the C strictly less than 4, then D3 of EVA equal to omega n. For our results in terms of the communication complexity, which improves the best known upper bound for the EVA function on the F2N and F2N compared with the two best known upper bound on the before. Our method we use here is using the combinatorial degeneration method. Our method can describe after the first we describe the cognitive preset problem as a hypergraph such that each cognitive corresponding to an S, and therefore the cognitive preset equivalent to the independent set in this hypergraph. And this hypergraph has a power structure, and therefore finally we propose the general method for constructing the larger independent sets in the power of hypergraph. And the method we use is the combinatorial degeneration. Okay, let me recall the definition of the hypergraph and the independent number of hypergraph. Here we consider the directed hypergraph, namely we focus on the three uniform directed hypergraph with the vertex FP, and each S set is the order triple of the vertex. An independent set in S is the subset of vertex V such that the S does not contain any endpoint of S. And the size of the largest independent set is called independent number of the hypergraph, and we denote it by the alpha of E. Now for the cognitive problem, we construct the hypergraph as follows, with the vertex set of hypergraph equal to F2N times F2N, and the each cognitive in F2N times F2N is equivalent and the N equivalent to an axis of the hypergraph. For example, with n equal to 1, we have the V equal to F2 times F2. Therefore, we have the 4 vertices, and we also have the 4 axes because on F2 times F2 we have the 4 cognitive like this. Therefore, by the construction, we have the independent set are equivalent cognitive preset. That is the independent set in hypergraph is the cognitive preset in the F2N times F2N. Now, if we consider the cognitive in F2 times F2 like this, now if we multiply the cognitive, another cognitive in F2 times F2, we will obtain another cognitive. Here we consider we multiply by consider the Cartesian product between two cognitive. So, or if we multiply with triple cognitive, that means lambda equal to 0, we also obtain another cognitive in the F22 times F22. In other direction, is the cognitive F22 times F22, we can write as the product between the two cognitive on the product of the cognitive with the triple cognitive. Therefore, our hypergraph defined on the cognitive problem has the power structure. That means the graph created by the by the cognitive on the F2 Mn times F2 Mn is the product of the graph defined on the F to N and the product with the graph hypergraph F to N. Before the present our technique, I will present the case for the directed acyclic graph. On the directed acyclic graph with at A and the vertices V, then we can construct the independent set on the n copy of the acyclic graph has a size at least V power n minus small o n. The idea is follow, because the acyclic graph, we consider the agency matrix of the acyclic graph. Here we put all diagonal on the agency matrix equal to 1, because acyclic graph, therefore by relabeling we can then the agency matrix of acyclic graph is the upper triangular matrix. Now if we take the n power of the agency matrix, this is the agency agency matrix, and then this is the agency matrix of the n power of the acyclic graph, because we put the all diagonal to 1. This is the reason. Therefore, now if we consider the submatrix indicated by the uniform and tuple string, then we can, because our matrix is upper triangular, therefore we on this on the subset indexed by the uniform and tuple string is identity matrix. And because the n is the independent set, when we restrict is from the agency matrix, it is the identity. Therefore, the size of the independent set is at least the size of uniform string in n tuple. Therefore, the size is at least V per n minus small o n. Okay, for acyclic graph, we have the topological ordering on for the acyclic graph. Namely, we can assign each vertex by integer number such that if we have an Ij, then Ai bigger than Ij. For the A is the vertex labeling map, or this can be equivalent to the exist two vertex labeling map AB such that they are equal to 0 on the vertex I, and AI plus Bj bigger than 0 if the Ij is an S, by we picking the map B equal to minus A from this definition. Now we can generalize this condition for the hypergraph. Now for the 3 uniform directed hypergraph, and let S be any subset of vertex set V. Suppose they are the 3 maps U1, U2, and UV, U1, U2, and U3, such that they are equal to 0 for the all vertex on the S, and they are strictly bigger than 0 for all the vertex in the V minus S, and they are strictly bigger than 0 for all the S's. Then we can construct an independent set on the n copy of the hypergraph has the size at least S power n minus small o of the n. Here is an example. If we take the hypergraph with 3 vertices 0, 1, 2, and the 3 axes like this. Now, if we take the S is the vertex set 0, 1, 2, with the vertex labeling like this, we construct as in the table. We have they are equal all on the vertex S and positive on the S set. Therefore, in this hypergraph, if we take the n copy of this hypergraph, we can construct the independent set of the size at least 3 power n minus small o n. The idea for the proving this theorem as follows. For the each hypergraph, we can construct the agency tensor for the hypergraph. In this, similar to the asymmetric, we put the O diagonal a tensor equal to 1. But because we put the O diagonal tensor equal to 1, then if we take the and copy and tensor power of the agency tensor, this also the agency tensor of the n copy of the n copy of the hypergraph. Now we restrict the agency tensor on the uniform string indicated by the n tuple uniform string. Here is we consider each element in the set S. Then we will obtain identity tensor. Because we obtain the identity tensor, that means the size of the independent set is at least the size of uniform string contract from the set S with the length n. Okay, why we obtain the identity tensor here? Suppose that we not obtain the identity tensor. That means there exists the 3 uniform string from S such that they form the 1S in the n copy hypergraph. Suppose the 3 string is A1, A2, and AN, B1, B2, and BN, and C1, C2, and CN. Now, if we apply the vertex labeling on this, define U1, U2, on U3 on the 3 string like this, because there is 1x between them. That means there is index I such that AI, BI, CI is an F in the hypergraph. Therefore, there is the row here sum the strictly bigger than 0. Therefore, the sum of all of them strictly bigger than 0. But because they have the uniform string, so the sum of all of them equal to 0. We have the contradiction. That means that there is no F between the 3 uniform string. Okay, for the Copenhagen process on the FP, and the first we construct the hypergraph on the FP for the each P equal to 2, 3, 2, and 3. Because now we from this theorem we can want to the construct the subsets, find the subset S of vertices as possible, such that there is a three maps satisfy the condition, and find the subset S satisfies the condition can be formulated as an interlinear program. So therefore, we consider the problem on the F2N and F2N, and for the F2N we take on the 3 copy, and we can find the subsets with the size 39 by the interlinear program, and the 1 copy of the F3 we can find the largest subset equal to 7. Therefore, we have the low bound for the largest corner preset on the F2N and the F3N. Okay, because we have the we can construct the larger corner preset on the F2N and the F3N. Therefore, we can impose the upper bound for the communication complexity on the EVA function on. Okay, let me stop here. Thank you for your listening.